we start discussion on a new type of higher pair mechanism which are very commonly used, and I am sure all of you must have seen this mechanism, which are called gears. Gears are nothing but, as you know, are toothed wheels. These are used all over the machines to transmit constant angular velocity ratio between two shafts. Let me emphasize, for transmission of constant angular velocity ratio between two shafts. Actually, pair of gears is used. One gear is mounted on one shaft, let us say the input shaft, and the other gear is mounted on the other shaft, that is the output shaft. So, pair of gears are used to transmit a constant angular velocity ratio between two shafts. I want to emphasize this constant angular velocity ratio. This is very different from constant RPM ratio. RPM is not angular velocity, that is the average angular velocity or average angular speed. But gears are used such that at every instant, the instantaneous angular velocity of the two shafts maintain a constant ratio. That is why we used gears. These two shafts can be parallel between two parallel shafts or intersecting shafts. That means the shaft axis might be intersecting at a point or even skewed. They are neither parallel nor intersecting. The spatial disposition of these two shafts can be either parallel or intersecting or skewed, and they can be connected by a pair of gears to transmit constant angular velocity ratio. To start with, we take a very simple type of gear to connect two parallel shafts, which are called spar gears, and that too with straight tooth. That means the tooth on these wheels are parallel to the axis of the shaft, which are these wheels are cylindrical and the teeth are cut on the surface of the cylinder, and these teeth run parallel to the axis of the cylinder. For such spar gears, as we see, the cylinders in a projected view, if we view it from the front along the axis of the shaft, we see just circle. So, these are called circular gears. So, instead of cylinder, I will use the word circular. To start with, let me define all the terms which are used for this description of gears, gear geometry, and gears transmission. So, we start with nomenclature of gears, by which I will define all the relevant terms with reference to circular, straight spar gear. So, now onwards we may not emphasize that we are talking of all the time circular straight to spar gears, that will be assumed. Later on we will talk different types of gears which are not circular straight to spar gears. Let me now show you with a figure how these a pair of two wheels which are circular straight to spar gears transmit motion from one shaft to another, maintaining a constant angular velocity ratio. This figure shows a pair of spar gears. As you see, the teeth on these gears are parallel to the axis of these shafts. These are the teeth, these are gear blanks. On the surface of this gear blank, the teeth are machined. And this is one shaft on which this gear is mounted. This is another shaft where another gear is mounted. You see, this is called external gearing. This kind of gear connection is called external gearing, and as it appears, these shafts along with this gear rotates in the clockwise direction, then the mating gear and the connected shaft will be in the opposite direction. So the direction of angular rotation is reversed due to this external gearing. Similar gears can also be used in internal fashion such that one gear drives the other in the same direction, maintaining the constant angular velocity ratio. This is the tooth of the gear and the blank or body of the gear. This figure shows a pair of internal gearing. There are two shafts. There is a bearing between the frame of the machine and the shaft containing this gear 1. There is a revolute pair here. This is gear number 2, which has a revolute pair with the fixed link. So this constitutes a 3-link mechanism. And as we see, if this I call gear number 1, I call gear number 2, the teeth are cut external surface of gear number 1 on this blank. Gear number 2, the teeth are cut or machined on the internal surface of gear number 2, and this teeth of gear 1 gets into engagement with the teeth in this case of teeth of gear number 2. And as if gear number 1 rotates in the clockwise direction, it also is gear number 2 in the same direction. So this is what we call internal gearing. So we have external gears and a pair of internal circular gears. Now let me define different terms to circular straight tooth spar gears. This figure again shows a pair of external gearing connecting parallel shafts, one at O1 and the other at O2. The smaller of these two gears, that is here number 1, the smaller gear is called pinion, and the larger gear either wheel or gear. Now let us observe these two circles which are drawn on gear number 1 and gear number 2 touching each other, and the centers of these gears are at O1 and O2 respectively. These two circles touch each other at this point. Let me call this point P. As we see, due to this external gearing, clockwise rotation of this gear is converted to counterclockwise rotation of these gears, and the angular velocity ratio omega 1 by omega 2 is constant. Exactly the equivalent transmission is also possible by mounting two friction discs, one disc of this radius and the other disc of this radius. Imagine two friction discs with center here and radius this much, and another center here and radius this much. Now, if we imagine these two friction discs, then one can drive the other without slip, then the same angular velocity ratio is transmitted. That means omega 1 by omega 2, if I call this radius say rp1 and this radius rp2, then this constant is nothing but minus rp2 by rp1, because there is no slip. So, at this contact point their velocity is the same. So, rp1 into omega 1 must be rp2 into omega 2, but omega 1 and omega 2 are in opposite direction, that is taken care of by this negative sign. These two imaginary circles, these circles do not exist in gear, these two imaginary circles are called pitch circles. And as we will see, most of the gear tooth geometry will be referred to these imaginary pitch circles. Now, let us imagine that this rp2 is made larger and larger, and ultimately rp2 tends to infinity. If rp2 tends to infinity, then this pitch circle is converted to a straight line, and such a gear whose pitch circle radius is infinite is called a rack. And this is the pinion which can also engage the rack, where this rp2 is infinity and we have a straight line instead of this pitch circle. Such a rack and pinion arrangement are very normally used, very frequently used to transmit constant speed from circular speed to linear speed or linear speed to circular speed. That means a rack and pinion is very often used for conversion of uniform angular motion to uniform rectilinear motion, or the other way around. If I drive the pinion, then the rack will have uniform linear motion, and if I drive the rack, then the pinion will have constant angular motion. So, for conversion of uniform rotary to linear or linear to rotary motion can be achieved by using a rack and pinion arrangement. Let me now define different terms of gear tooth geometry with reference to this figure. We have shown two adjacent teeth of a gear and one tooth of the mating gear. This dotted line shows the tooth of the mating gear which is in contact with this gear, of which we have shown two consecutive teeth. This circle is the pitch circle, this circle refers to the pitch circle of this gear. This width along the axis of the shaft, that is called face width of the gear, and this circumferential distance measured along the pitch circle between two adjacent teeth, the right hand face and the left hand face, this is called space width. This surface where the contact takes place, as it is taking place here, this surface where the contact takes place, that is called the face of the gear. This is face of the gear, this is face of the gear. On the face of the gear, the portion above the pitch circle, that is this portion, that is called face, and this is the below this pitch circle, this is called the flank. And as you see, there is a little fillet to connect to the body or the blank of the gear. The portion above the pitch circle level is called face, below this is called flank, and the flank is connected to the body of the gear through fillet. This outer circle, if we imagine an outer circle passing through the top outermost surface of this gear, that circle is called addendum circle. Similarly, this bottom circle, which belongs to the body of the gear where the teeth ends, this is called the dedendum circle. The thickness of this tooth, as you see, it varies from the bottom to the top. If this thickness is measured along the circumference of the pitch circle, that is called circular thickness at the pitch circle. The circular thickness keeps on varying. It is maximum here and here it is minimum. As you see, we must prevent the rubbing of this top surface of the mating gear with the bottom surface of this gear. So, if this is the addendum circle of the top gear, this is the top surface from the center of that gear. If we draw a circle, that will be the addendum circle of the mating gear, and it is this distance, if measured along the radius of this circle, that is called clearance. The radial clearance between the addendum of the mating circle and the dedendum of the other gear, addendum of the one gear with the dedendum of the mating gear, this radial clearance is called clearance. And if we measure the radial distance between this addendum circle of gear 1 with the addendum circle of the mating gear, that is this distance, this circle refers to the top surface of this tooth, this circle refers to the top surface of this tooth, the mating tooth, and the radial distance between them is called working depth. If we measure the distance along the identical points of two adjacent teeth of the same gear and measured along the pitch circle, that is from here to there, this is one point on this tooth, I go to the identical point of the next tooth, that is here, then this distance measured along the pitch circle is called circular pitch. If I call it P, this distance measured along the pitch circle, then PP is called circular pitch. The radius of this pitch circle we have already denoted by R P. We also define something called diametral pitch. By diametral pitch, we mean the number of teeth per unit length of the pitch circle diameter. If the number of teeth is n, then n by 2 Rp that is number of teeth by the pitch circle diameter. 2 rp is dp, the pitch circle diameter. This is called diametral pitch. And what is this circular pitch? It is easy to see. This total perimeter of this pitch circle will be 2 pi rp. And if there are n teeth on this gear, then pp will be 2 rp by n, where n is the number of teeth. So 2 pi rp by n, that is pp. From these two relations, diametral pitch we write as, say, dp. So if we multiply pp by dp, as we see n and 2 pi cancels, we get pp into dp is nothing but pi. The inverse of the diametral pitch, which is more commonly used these days rather than the diametral pitch, is called module. Module of the gear tooth. And all mating tooth have the same module. Module is nothing but inverse of the diametral pitch, that is twice rp by n, where rp is the pitch circle radius and n is the number of teeth, which clearly tells that this pitch circle radius are proportional to the number of teeth for a pair of mating gears, because module is same. That means rp1 by rp2 is rp by n is constant, so n1 n1 by n2. rp1 by rp2 is n1 by n2. We have already seen the angular velocity ratio omega 1 by omega 2 was minus rp2 by rp1, which means minus n2 by n1 for a pair of external gears. So the angular velocity ratio is inversely proportional to the number of teeth in the gear, with a negative sign for external gearing and with a positive sign for internal gearing. We have given so far various definitions which define the tooth geometry of circular gear, like pitch circle radius, then circular pitch, then diametral pitch, then module. We have also defined addendum circle, and the difference between the radius of the addendum circle and the pitch circle is called addendum. We indicate it by the symbol A. A is called addendum. Similarly, we defined the dedendum as rp minus the dedendum circle radius, say rb. This is what we call b, and that is what we call dedendum. This A and B, everything is finally standardized because gears are used universally. So they are standardized according to various standards, and A is normally of the order of m and B is greater than A. Typical values of the standards we will discuss much later. What you should know, that to have that clearance, B should be greater than A, and A is of the order of module. Next, we should discuss what should be the tooth profile such that the constant angular velocity ratio is maintained. So we have a higher pair, there is a line contact between the a pair of teeth of the mating gears. Now, what should be the tooth profile such that constant angular velocity ratio at every instant is maintained? This is what comes from what we call fundamental law of gearing. To discuss the fundamental law of gearing, let us say one gear has this revolute pair with fixed link here, and the other gear is mounted there, that is the revolute pair of the second gear mounted to its bearing. Now, the question that is asked, suppose this is one gear, a rigid body, and this is another gear. What is the condition necessary such that these two gears maintains a constant angular velocity ratio? So, let me say this is fixed link 1, this is gear body 2, this is another gear body 3. So, this revolute pair obviously is the relative instantaneous center 1, 2, and this is the relative instantaneous center 1, 3. Now, the question is where is 2, 3? 2, 3 we do not know where, but definitely lies on this common normal. If I draw this common normal, then 2, 3 lies on this line n n. Applying Aronhold-Kennedy theorem, we know that 1, 2, 1, 3 and 2, 3 must be collinear. So, if we draw the line 1, 2, wherever it intersects this line n n, this must be the location of 2, 3. Now, if this gear rotates in this direction, at this instant the angular velocity is omega 1, and this gear rotates with angular velocity omega 2, let me call this point of intersection 2, 3 as P. 2, 3 means the velocity of this point considered to be a point on body 2 must have the same velocity if I consider this point P to be a point on body 3, which means omega 2 into, if this point I call O2 and this point I call O3. O2 is 1, 2, O3 is 1, 3. So, O2 P into omega 2, sorry, this I called omega 1, let me call it omega 2, and this let me call omega 3. Because body 1 is the fixed body, I am representing one of the gears as body number 2, so I denote it by omega 2, and the other gear as body number 3, so I call omega 3. So, omega 2 into O2P in this direction must be same as omega 3 into O3P. I consider the velocity of the point P to be a point on body 3, then its velocity due to this omega 3 is again in this direction, which is perpendicular to this line O2, O3, which is omega 3 into O3P, which tells me omega 2 by omega 3, where omega 2 I have measured clockwise and omega 3 I have measured counterclockwise. So, there is a negative sign involved here, which is nothing but O3P divided by O2P. Now, if omega 2 by omega 3 I want to maintain constant, O2 and O3 are fixed point, then this point P also must remain fixed. Then only omega 2, the shape of the body should be such that the common normal always passes through the same point P on the line O2, O3. this line O2, O3 is called the line of centers, and this line P is called the line of action, which is the common normal between the mating surfaces. So, for omega 2 by omega 3 to remain constant, this point P must not move, this point P must be a fixed point on the line O2, O3. And this relationship is called fundamental law of gearing, which in words I can express as the common normal which we call line of action must intersect the line of centers that is O2 and O3, line of centers. O2 is the center, O3 is the other center of the gear. The line of centers, the common normal must intersect the line of centers at a fixed point. Then only the constant angular velocity ratio is maintained, and this is known as fundamental law of gearing. This fixed point, as we will see, will be called pitch point. Next we shall discuss there are various profiles which are possible to maintain this fundamental law of gearing and maintain this constant angular velocity ratio. But as we know, most commonly it is the involute profile which is used for the gear tooth. Now let me see what is an involute. As I said just now, gear tooth profile should be such that they should satisfy this fundamental law of gearing. Actually, these profiles which satisfies the fundamental law of gearings are called conjugate profiles. In fact, if one profile is given, whatever the arbitrary, so long it is continuous, we can always find another profile which is conjugate to the given profile, such that the fundamental law of gearing is satisfied. But that is not what is used in practice. In practice, we use what is known as involute profile. Most common gear teeth are of involute profiles. As we will discuss subsequently, these involute profiles has lot of advantages, including the manufacturing facility, fabrication advantage, convenience. We always normally use involute profiles. Now let me discuss what is an involute. Involute of a circle is defined as follows. Let us talk of a circular cylinder, say of radius r, and think of a string which is wound around this cylinder, a string or tape which is wound around this cylinder. This is the end of the tape. And now if I unwound this tape from this cylinder, keeping this tape or the string always taut, I am unwinding this tape and keeping the tape always taut. That means this portion of that, this is the tape which has been unwound, which was originally on the surface of the cylinder, and now it is being unwound. So this is the tape at one position, this is the tape at another instant, this is the tape at another instant. At every instant the tape will be tangential to this original cylinder because it is kept taut. Then the end of this tape, the curve that is generates is called involute of a circle, because initially the tape was wound on a circle. That's why you can define involute of any curve. That means originally the string was wound on that particular curve, but we are not interested in anything but involute of a circle. And this circle from which the string is being unwound is called base circle. Base circle of this involute. and we shall denote it, the radius of the base circle, by RB. And this is the involute of this base circle of whose radius is RB. Then let us show from a what we call a crossed belt and pulley analogy to explain why this involute profile will satisfy the fundamental law of gearing, or a pair of involutes will be conjugate profiles. That we shall discuss from what we call a cross belt and pulley analogy. As I said just now, let me now explain how a pair of involute tooth profiles can maintain conjugate action, that is, they can transmit constant angular velocity ratio satisfying the fundamental law of gearing. This we shall do by an analogy with a pulley and cross belt drive. Let us say this is one pulley, pulley number 1, which can rotate about the point O1. Similarly, this is again another pulley, which is pulley number 2, which can rotate about this axis at O2. This common tangent between these two circles representing a pair of pulleys represents the belt, one side of the cross belt. You can imagine another common tangent on this side, which will complete the cross belt. So, this is a cross belt overlapping this pair of pulleys. Suppose the pulley number 1 rotates in the clockwise direction with angular speed omega 1. If we assume there is no slip between the belt and this pair of pulleys, then the speed of any point of the belt is given by R1 omega 1 in this direction, where R1 is the radius of this pulley number 1, that is, this is R1. Because there is no slip between the pulley and the belt, the angular velocity of this pulley omega 2 will be such that the speed of the belt is also equal to R2 omega 2, where R2 is the radius of this pulley. So, this cross belt and a pair of pulleys transmit constant angular velocity ratio between these two bodies, namely 1 and 2, where omega 1 by omega 2, if we take care of the sign, this is clockwise, this is counterclockwise. So, from this relation we get minus R2 by R1. At this stage, let me imagine a pencil connected to a particular point on this belt, say at this point Q. If I attach a pencil here, as this belt moves, this particular pencil will draw this straight line AB. It will start from this point Q was sometime before at A, and as the belt moves, the pencil moves along with the belt and draws this line AB in this piece of paper or in the fixed space. Let us now try to imagine if I attach a body which is integral to pulley 1. This is an extension of pulley 1, that is pulley 1, and this is same rigid body. What is the curve drawn by the same pencil which was attached to this belt on this body, that is here? To find out, determine that particular curve which is drawn by the pencil on body 1, what we do? We hold the pulley 1 number 1 fixed. If we do not allow the pulley 1 to rotate, then this string which is unwinding from this pulley unwinds in the counterclockwise direction, because the pulley was rotating in clockwise direction and the belt was straight. Now, if we hold the pulley fixed, then the belt as it unwinds rotate in the counterclockwise direction. So, as a result, this point Q on this belt or string generates an involute of which this pulley is the base circle. That is, this circle represents the base circle of this involute. This particular point, when Q was here, this particular point of the pulley was there. When the Q has moved down by the distance AQ, this point on the pulley, because the pulley is rotating in the clockwise direction, has moved there. So, the same pencil which is drawing this line AB in space or in the piece of paper, fixed space, is drawing this particular involute on this body 1. This circle represents the base circle of that pulley, base circle of this involute, and this is the string which is generating the involute. Exactly using similar logic, we can say the same pencil attached to the Q will generate this involute on this body. This is an integral part of pulley 2. This is rotating in the counterclockwise direction. So, if we hold the body 2 fixed, then I see the string which is winding on this particular cylinder should wind up in the clockwise direction, because this was not moving, this was not having any rotation, this was rotating in the counterclockwise direction. So, if I hold this fixed, this winds up and also rotates in the clockwise direction and generates this involute. Now, if we cut this body along this profile and this body along this profile, then this involute I can have here. Now, the point of contact between these two involutes is always on this line. And if we remove this belt now and rotate this body 1 in the clockwise direction, as we see, this involute will push this involute in this direction and this will rotate in the counterclockwise direction, maintaining exactly the same relationship as it was doing when they are driven by this belt, when they are connected by this belt. So, exactly identical motion between this pair of pulleys with the cross belt can be achieved by cutting an involute profile on body 1 and an involute profile on body 2 and allowing one involute to drive the other involute. Again, omega 1 by omega 2 will be given by minus R2 by R1. Thing to note is that as this body rotates, the point of contact changes on both these profiles, but it will always lie on this line AB. A further clockwise rotation will make counterclockwise rotation. This point may come in contact with this, but both of these points will lie on this line somewhere. So, this line AB, which is normal to these involutes, because this is the string, this is the involute. So, at every instant the string is perpendicular to the involute. So, this line AB, which is common normal between these two involute profiles, defines what we call the line of action. This line AB, what we call line of action, and this line of action AB intersects the line of centers at this point, fixed point P. So, let me repeat, these are the two involute profiles which maintains the same motion as was being done by this cross belt. If we remove the cross belt and allow this involute to drive this involute, then this angular velocity relationship, constant angular velocity ratio, is maintained. The point of contact moves along the line AB, which we call the line of action, and this line AB is the common normal at the point of contact to the pair of involute. This is the line of action, and this point P we call pitch point. P is what we call pitch point. Finally, let me complete the sentence that using this analogy between a pair of pulleys driven by a cross belt, we have shown that a pair of involute profile can maintain the same conjugate action, that is constant angular velocity ratio, even if we remove the belt, because a point on the belt which is generating this line AB in space are generating a pair of involutes on body 1 and body 2. Let me continue our discussion with this belt pulley analogy. As we have seen just now that this is pulley 1 of base circle radius RB1. This is pulley 2 which is the base circle radius RB2. This AB is the common tangent which represented the belt, and these are the two involute profiles which, as I said, can be machined on body 1 and body 2 and remove the belt, and rotation omega 1 through this involute profile will cause rotation angular velocity omega 2 of body 2 through this contact between these two involute profiles. By the very construction, if this is the string which is always taut and this point is generating this profile, it is obvious that this line AB is normal to both of these involute profiles. That is, this common tangent AB between these two base circles is the common norm to these involute profiles, which means this is what we call line of action, which is the common normal between the profiles. And this common normal is intersecting the line of centers O1, O2 at this point P. And as you see, because of these base circles, this point P never changes as these two belt rotates, because this always remains the line of action. The common normal, when the contact is here and here, anywhere, at this point the contact is shown. As the gear rotates, the contact changes from here to there, but this common normal always remains the same. And it is this common normal which intersects the line of centers O1, O2 at this point P, which is fixed point, which is not changing. So this point P we called pitch point. So this clearly establishes that these two involute profiles maintains the conjugate action, because the pitch point is fixed. It does not change on this line O1, O2. It common normal AB intersects O1, O2 at this fixed point P. And if I draw these two circles with O2P and O1P as radius, these represents nothing but pitch circles. This and this of radius RP1 and radius RP2 are pitch circles. The angle that this common normal AB makes with the common tangent to these two pitch circles, TT, is the common tangent to these two pitch circles of radius RP1 and RP2. The angle that this common tangent AB to the base circles makes with this common tangent to the pitch circle, this angle phi is called operating pressure angle. It is obvious, if this angle is phi, then this angle is also phi. Similarly, this angle is also phi. O1A is the radius, this is the point of common tangency A and B. So angle between O1A and the vertical line is same as the angle between AB and this horizontal line. So this is phi pressure angle, this is also phi the pressure angle, and this angle is also phi the pressure angle. So what we see, that RB2 is nothing but RP2 cos phi, because this angle is 90 degree. Angle between the tangent and the radius is 90 degree. Similarly, this angle is 90 degree, angle between the radius and the tangent, and this is RP1 and this is RB1, and the angle between them is phi. So what we get, RB2 is RP2 cosine phi, where phi is called the operating pressure angle, and RB1 is RP1 cosine phi. So the angular velocity ratio omega 1 by omega 2, which we earlier have seen as minus RB2 by RB1, is also equal to minus RP2 by R P1, because if you divide this by this, cos phi cancels, we get this. So, we have defined operating pressure angle, the pitch point, the line of action for these two involute profiles maintaining conjugate action. In our next lecture, we shall discuss what are the advantages of such involute profile.